During this next session, we're honored to introduce Darren Berns, Chief Technology Officer of IDEX Optical Technologies. IDEX Corporation, with over 7,000 employees globally, is a key player in applied solutions for critical sectors. The company's innovations in photonics drive advancements in precision healthcare, industrial manufacturing, and environmental technologies. Darren Berns, a leading authority in optical technologies, has been instrumental in the rapid advancement of photonics and optics capabilities at IDEX, particularly in high-precision applications. His leadership ensures the company's global competitive edge, plus its ability to meet the increasingly complex demands of modern industries.
I'd first like to thank the entire staff of Optica. Thanks again for the opportunity to present today. And also thanks to all of the previous presenters. So I guess I've got good news and I've got kind of in the middle news. So the good news is I'm the last person between you and a award ceremony and then dinner. So I'll try to be brief but on point. And then the medium news, I didn't want to say bad news, but the medium news is I'm going to take us back to the Cambrian period from the comments made earlier. And I actually made a few notes based on some of the phrases that were used, which I think is really useful, right? So we spent a lot of time today talking about what is inevitably the future of photonics and the future of photonics manufacturing. But I'm here to say that there are a lot of problems to solve still today and for the next 5 years, really, in small to medium volume, optics manufacturing, discrete optics manufacturing off the wafer, right? And it would be great if every single application was high enough volume and at the right point in the technology readiness level, and at the right power level so that it could be used, you could build a photonics chip on a wafer and it would solve all your problems. I think the reality is that that's not true, right? It will be true for a lot of applications that we've all envisioned, but there are a lot of things in front of us today that don't fall into that category. And so there are a lot of businesses like IDEX and others who are really focusing on how do we solve those problems today, and how do we build manufacturing capability that will be useful for certainly the next 5 years, perhaps the next 10 years, with an eye towards that future of us connecting electronics and optics in a way that we all hope to as we go. So a few of the phrases I heard, which are useful, and also I'll say that, sorry, I'll start over, with 3 key points. So I hope you take away 3 things today, and I'll start with the first one, and then we'll dive into the content. The first one is what I just said. Discrete optics is still alive and the current challenge for many, and that's going to be a point that we go. And so with that, Ashkan, who was here earlier, said a few things. One was, why don't we make awful solutions work first? That was an interesting phrase. I appreciate that. And in large part, that's actually true, right? You can't always get to the best possible solution right out of the gate. And sometimes the solution you have is good enough, right? We at IDEX use a term called 80-20 all the time, right? And it's, another way is focus on the critical few. And there's a bunch of businesses, I think, that follow similar logic. But the general idea is don't kill yourself for the last maybe 20% if you're already 80% of the way there. Make it work and get it in people's hands. And then listen to the market. Right? Listen to what people have to tell you. You know, in many places and in marketing terminology, people talk about minimally viable product, right? And why do you do that? Well, it's because you may not be right. You know, you may believe you have the solution that someone's asked you for, but until you put it in front of them and you put it, in their face, they can't give you the feedback that you might need through that voice of customer to really know. So another theme I'll talk about a little bit later is getting to the problems to be solved in the market from the customers, and then make sure that we balance our technology development versus those problems to be solved. So that's point number 2. There's another phrase, I'm going to use you again, Ashkin, that think of optics as a transmission line, with the idea that using optics can be as simple as thinking about it as transmitting information, but just doing it through a different pipe. IDEX, and I'll show you this in a second, we started out as a fluidics company, and now we have a considerable position in photonics. We think of them kind of the same way, right? We use the fluids analogy all the time when we talk about the flow of light, because in many ways, it's kind of the same thing, right? We in fluidics, we have pumps, we have valves, and boy, if you ever want to talk to your children about optics, just use plumbing, right? They understand plumbing, usually, so you can talk about it from that perspective. It works for me and with my kids, so I recommend you do the same thing. But the challenge I bring to all of us is, what if it's not information you're transferring, but energy? And what if that energy is really high? So I'm going to show you a couple of applications here at the end that really get into that bucket. And we just heard a wonderful description of laser fusion, and that falls into that bucket, but at the highest extreme level, right? Trying to transfer energy to a very small volume in the right way so that it actually can be used and combined into something else. That presents a problem. It presents a problem for this semiconductor model, I believe. Please tell me if you think I'm wrong. But it means that if you think the fluid analogy again, what if all of a sudden the pressures were really, really high and the temperatures were really high and you're trying to still shove the same fluid through the same pipe, right? It doesn't work at some point, right? Or if the pipe has to be really long, like let's imagine it has to go through space and it's 100 kilometers of free space. That's a different problem too. So I think when we think about photonics and optics in general, I think we have to step back and think about that broader vision. And someone said it a little bit earlier about let's open up the party, right? Let's talk about all the potential photonics applications. And I think what that does for us is it helps us go from where we're at today to where we will probably ultimately be with combining electronics and photonics 10 years from now, 15 years from now. But there's the place we have to go from here to get there. And in many ways, that's going to be the challenge of how do we scale current manufacturing solutions to kind of this medium to high scale, all right? And even then, boy, wouldn't we all love in the photonics world, Chuck's over here, wouldn't we all love to be back in the telecom boom and bust, right? I remember in 1998, we had people calling us at a former company, Research Electro-Optics, where I was at, just begging us to make another manufacturing line for pentaprisms, right? And we were kicking out 20,000 pentaprisms, these discrete optics every week, and then it was higher and higher, and it was sort of like, can you spin up manufacturing, conventional manufacturing, fast enough to meet the needs of the market? And that honestly just hasn't existed since that time, right? That boom and bust, the bubble of the telecom, datacom world died, and we went from millions and tens of millions of discrete components to, boy, if you're lucky today, it's 10,000, maybe 100,000 if you're really lucky. And so what we've talked about all day today and what we've talked about this morning is an awesome future, and I think we're going to get there, but it's going to still take some time, right? And it's going to take a period of sticking with the problem, to use Chuck's phrase earlier, that we've all talked about. But in the meantime, there's problems to solve today, and hopefully I can give you a little bit of perspective on that in the next 10 minutes or so. So who is IDEX? You might have heard our name. We're roughly a $3 to $4 billion company, founded in 1988, 8,000 employees. Most people have never heard of us. I always say we're like the BASF, if you ever saw those commercials, right? We're inside of everything that you do. And that's really true, and I'll show a couple of applications of that. This is another picture. These are all meant to be the companies that are part of IDEX. And when they were acquired by IDEX, starting in '89 and going out to 23, there's two additional companies that aren't on this list that were recently acquired by us. But it's really the tale of two companies, and I only tell you that to give you perspective on who IDEX is so that maybe some of the things I'm saying can kind of come with some background. But the first company was kind of until around the 2010 range, and that was we were an aggregator and an acquisition-based holding company. We would buy companies that were profitable in industries that was very industrially focused. And again, fluidics, Hale, Viking Pump, Warren Rupp, these are like big oil rig, water truck pumps, and valve systems, but all for the intention of moving water and other fluids around. That was company number one. Company number two has really been in the last 10 years and probably more so in the last 5 years. And I think this gets to a lot of the themes that we've been talking about, and that is, how do you start to build a platform of businesses that ultimately can solve a set of critical problems because you have the critical mass to do it? And so you see on this list CVI, Melis Griot, they're part of IDEX, Semrock. There's a number of optical coating companies, a number of fabrication companies that are part of this list. But what I can honestly say, and we're quite proud of, is that there's only one or two of the companies on this list that are no longer part of IDEX. So they are brought into the business based on a strategic vision and then held there. Okay, global macro trends. We heard about this a bunch of different ways, so I won't dwell on it, but these are the things we really think are important. And we heard topics about this and comments about this earlier today. The one in the middle we didn't really talk about that much, but I'm here to say that it is an immediate challenge for us in this industry, for many industries as well. There are issues, we talked about issues associated with regulation, the CHIPS Act. I've been around long enough in this industry that it used to be that the only regulations that were really in the way of us transferring technology or product across from the United States to Europe were in the defense sector, for obvious reasons. That's no longer true, right? Chips, even designs for tooling that's associated with the manufacture of products for either the defense industry or now the semiconductor industry is also limited. We're probably not very far away from the life science sector being limited as well in terms of how do we transfer technology and information across borders. And since so much of the money, big money, is coming from the United States, this should be a cause for concern for all of us, right? How do we maintain the level of communication that we've all talked about in a world where the regulations are pressing down on us, right? And so I think that's a little bit of a takeaway. Is how do we deal with that as we move forward? Okay, so what do we bring to the table? Whoops, let's go this way. So IDEX is really good at building platforms, leveraging technology with an innovative spirit and large capital backing. We, as I said earlier, we focus on the critical few and really try to focus on growth. And then it's really bringing this strategic vision to the table. So with that in mind, we think about things from this perspective: product positioning, innovation, operational excellence. These two on the right side, the balancing act between those is a challenge for everyone. It's kind of that long-term versus short-term. How do you do the business of today? How do you meet the needs of a public investor base while you still think about what's going to happen in 5, 10, 15, 20 years? It's a problem, but it's as Chuck said, it's table stakes. Couple of key phrases I think are really important. I think we all know this, right? Lasers and optical technologies can change our lives. Optics manufacturing, I think, really, if we think about it, provides the toolkit to control light. We've heard that term a few times. And then innovation in a number of areas really help to drive those solutions. So impact across a wide range of markets. Here's my comic relief of the day. Not sharks with lasers, right? So anybody who saw that movie, you can have a chuckle with that. Okay, getting to the final 2 points here. So fundamentally, innovations in all areas lead to the most differentiated solutions, right? So we look at it from this perspective. It's everything. It's how do you focus on materials that get you to where you want to go? How do you make sure that you can make shapes out of those materials? And then how can you control what happens on the surface? So how do you functionalize the surface of this thing? So from an optical coating standpoint, it's a lot of things. We've been in the business of optical coatings for a very long time and really are industry leaders in this area, but we still don't know enough, right? And we need to know more. Fabrication of shapes, there's a whole bunch of topics we've talked about with so far. The one I'll mention down there at the bottom is we're actually starting to see a much bigger area of working with lasers interacting with materials to form things that then can help lasers work, right? So it's sort of that cycle of utilizing the technologies in a useful way. And then materials. We just had the gentleman up here from the glass manufacturers, but I'm here to say we need more, right? Glass has been the substrate of the last 100 years. Well, let's go back to a very long time ago. It's probably been for 1,000 years. But in reality, glass is primarily what we use for the most part for the substrates for materials, for the intention of creating curved surfaces for diffraction and refractive elements. Ceramics are potentially a future here. Nanocomposite ceramics offer the ability to create mechanical properties that you want and optical properties that you want as well, and so we're focused on that. Lastly, I'm going to get to 2 or 3 examples here, and then I think that's it for my time. So again, we use this term a lot, jobs to be done. So laser communications and environmental sensing. What is the problem? Right? So when we go to our customers and ask them, what is the problem? You're trying to move light tens to hundreds of kilometers across space, isolate it and control it to 7 or 8 orders of magnitude. So I've got a really bright beam shooting out of one satellite, and it has to be collected by another satellite that's 50 kilometers away at 10 to the minus 7, right, or 10 to the 7 orders of the other light, right? So the ratio is really big. This is a problem we solved ages ago with fiber optics, optical isolators, right? But now you need an optical isolator that works on a satellite, and you need to do it in a way that you can control the end result. So it's also optical coatings. How do you get rid of the sun? You've got to be able to isolate your signal in a way that also blocks out the sun to the same sort of degrees of extinction. And then you also have to be able to deposit coatings on surfaces that are very thin, super weird aspect ratios, and they can't bend very much, and oh, by the way, they're really big, right? So 6-inch optics that have to maintain nanometer level precision, because otherwise it bends the light beam enough that by the time you go 50 kilometers away, it doesn't look like the light beam you started with. Another example, next generation sequencing. So what's really the job to be done? We're trying to isolate pixel by pixel information that tells us something about the assay that's been done or the genetic information that's on, say, a microchannel plate or even just a general flow cell. Doing that quicker, faster, and then getting to a point where you can extract the information. Requires large field of view, diffraction-limited objectives, flat top illumination. These are all problems that are associated with, for the most part, discrete optics that are put together. Can we do this ultimately all on a chip? Absolutely, right? And that's the future. You put everything on the same chip. You put the flow cell on the same chip, you put the detectors, you put the sensors, you put it all together. But for the most part, that still doesn't exist today. So this is the problem we're faced with currently. And then how do you deal with that? Well, now we have to create illumination that's uniform, that's flat, do that all in free space optics. And then this is probably the solution that lasts for the next 4 or 5 years, and then we move to chips, lab on a chip, photonics on a chip, et cetera. Last one I'm going to leave you with is semiconductor metrology. Again, this is one we all know very well, but part of that in situ metrology of the entire process is to image what's happening, either at the mask or on the wafer. We talked about EUV metrology quite a bit earlier. What we forget about is that we have to measure the mask to the same level of precision as the chip you're trying to make. Right? So if you're using EUV lithography and you have an EUV mask, now we have to look for defects, nanometer level defects on a wafer or on a mask at that same level of precision, and be able to move, by the way, this is the other part we forget about, but I'm a mechanical engineer, so I'll bring it up. You got to move the wafer with the same level of precision. Right? This is something we often forget about on the optics side, but there's an entire industry, and we play some part in that, but of just the mechanics associated with moving a wafer to nanometer level precision and then stitching all that information together, because it's still using microscopes for the most part to image them. And now all of a sudden, oh yeah, now the masks or the pellicles that go over the masks are also made of materials that no longer transmit deep UV light. They transmit EUV light. So the microscope needs to be an EUV source as well. So that presents all kinds of challenges. But in many cases, we can still do imaging on most of the wafer systems with traditional glass-based systems. And so the solution for a lot of that is optical fabrication and assembly processes today that allow you to align glass elements to within a fraction of a micron so that you can get a high NA objective that can image the wafer that you want. We saw earlier EUV lithography systems moving to higher and higher NA, right, as the evolutions go up. That's going to be true. Those are still free space optics, right? They're still reflective optics built by our friends at Zeiss and others. Very big elements, right, that all have to fit together. So fundamentally, I'll leave you with that third point, and that is I think it's really important for us all to really listen to the voice of customer, as we say. Hear that message. Think about how do we go from where we're at today to where we need to be and where we want to be 10 years down the road. And that's going to involve some solutions that automate and allow us to be better at our current jobs. And back to Ashkin's phrase, let's take awful solutions and make them better, right? Or however you said that. So anyway, thank you. I appreciate your time.
What a great day. Just one question for you. When we had this event in 5 years, what is your preferred future for the optics industry? How do you want the optics industry to look then?
Oh, well, I would hope that we're talking more. I hope we're communicating more. And this fits the theme, I think, of this discussion. We're still in a world where everybody's afraid to share information. It's just honestly true. And I would say it's the United States and Europe, I think, have different problems. The United States has a lot of money. There's a lot of funding for a lot of things. But nobody wants to share. Everybody wants to develop their IP. They want to hold it tight. Their investor base is giving them hundreds of millions of dollars. And they see their way of differentiating by keeping that IP close to the chest and not sharing it with anyone. I think Europe has a different problem. I think from what we saw today, there's a little more information sharing. There's a number of institutions that are built fundamentally to share information. but there's not the same level of funding to take those ideas and that shared information and scale it as fast as is often done with the capital that's in the United States. So how do we get the best of both worlds? That's really what I wish for this industry. Because until we get there, a lot of these questions we've had today about scaling, about finding the right solution at the right time, it's really hard to work through the noise of all of what everybody says and really understand what are the critical few problems. What are they, right? Because if you ask me, I've got a different answer than you do and than you do.
Thank you, Darren, for a great presentation. Thank you.